We have three keywords in this learning objective: calculate, interpret, and evaluate measures of central tendency and location to address an investment problem. We'll begin with some measures of central tendency. We're going to look at the mean, the median, and the mode. These are all terms you should be fairly familiar with. And what we're trying to establish is where the data are centered. In other words, the expected value. So if we had a bunch of observations and we took one at random, and if we had to guess what it would be, we would probably want to guess somewhere in the middle of the distribution. We can use the arithmetic mean, which is just simply the sum of all the observations divided by n. Describes a representative possible outcome. However, it is sensitive to outliers. A good example of that is, let's assume you have 10 people in a room all making $62,000 a year, and you put a billionaire in there. So you have 11 people in the room. The arithmetic mean would not describe any of them. Maybe closer to the billionaire than the other people in the room, but it certainly would not be a representative possible outcome. We can turn to the median for that, which is the middle value. This is not affected by outliers. So with 11 individuals in the room, the sixth person, if you rank them from highest to lowest, and you take the sixth person, you'd have 5 above and 5 below. The sixth person would have an income of $62,000. That would be representative of a possible outcome. So how we determine the middle observation, if you have an odd number of observations, it's n plus 1 over 2. Well, here we had 11. So 11 plus 1 over 2 is the sixth observation. If the billionaire wasn't in the room and we only had 10 people, if you have an even number of observations, it's the average of the middle two. So it would be n over 2 plus n plus 2 over 2. So again, with 10, you'd have 10 over 2 plus 12 over 2, which is 5, plus 6, which is 11. You divide it by 2, you get 5.5. So in other words, you take the fifth one and the sixth one, and you would take the average of them. That would be in the middle of 10 observations. The mode is the most frequently occurring value in a data set. So if you had 10 observations, as we have here, let's say that we had 20 observations instead, and 10 were 62,000, and you had 5 below 62 and 5 above 62, and you took one at random, you would say, well, 62 occurs most frequently. That would probably be a representative possible outcome. The data set, however, can have more than one mode or no mode at all. No mode means all observations are different, and all observations occur only once. So the mode isn't really going to tell you very much because there isn't anything there. If you have a distribution with a single mode, it is referred to as unimodal. If you have two modes, that is referred to as bimodal. Okay, from the chart at the top of the screen, some terms you should be familiar with: absolute frequency, relative frequency, the cumulative absolute frequency, and the cumulative relative frequency. For absolute frequency, this is just a count. This is the number of observations that you would see in each of these particular observation intervals. -5 to -4, there's one observation. -4 to -3, there are 7 observations. Hop on over to cumulative absolute frequency. It just adds them up on the way down. So 1 in the first interval, 7 in the second, which means we should be at a total of 8. We see 23 in the next interval. Add to the 8, we should be at a total of 31. For relative frequency, it's just the percent in each interval, and then this is just a cumulative percent. Pretty straightforward stuff. Outliers, what do we do with these? We can either do nothing. If the values are legitimate and correct, we can just leave them. The thinking behind this is that the data set with the outliers perhaps would not be that data set without the existence of the outlier. So for example, if we were studying the entrepreneurial and creative potential of a room full of people, it would be higher if that room had some very successful entrepreneurs as role models in there, because the other people in the room would be pulled towards that example, so that their existence actually changes the nature of the data in the room. So whenever we're looking at a data set and there are outliers, we have to ask ourselves, well, does the existence of the outlier change the nature of the other observations, such that if the outliers weren't there, would we have observed something different? Now, if the answer is no, if you remove the outlier, if it were never there, you still would have observed the same thing, then it is a legitimate outlier. It can be removed. By the way, if you do nothing with an outlier, it does eliminate that judgment call. You can delete the outliers. That would be what we've seen already, a trimmed mean. By the way, the reading gives an example of 5% trimmed mean, suggesting that you take 2.5% off of each side. That is wrong. A trimmed mean, if it's 5% trimmed mean, it means you trim 5% on both sides. You can replace the outliers, and that is a Windsorized mean, and we've already seen that. Whenever you do take outliers out, what you would like to do, whichever measure of central tendency that you're using, typically it would be the mean when you're removing the outliers, is you want to compare the mean with and without the outliers. Sometimes removing an outlier almost does nothing to the mean, in which case you can make the decision to do nothing. We can leave it there. Other times it has an outsized impact on the mean. And again, if it does not affect the likelihood of seeing the other observations as they are, then at that point you would make a decision of, okay, I'm going to do something about the outlier. Question is, am I going to delete it or am I going to replace it? Okay, let's move to measures of location called quantiles. And there are different quantiles you can calculate: quartiles, quintiles, deciles, and percentiles. I'm sure you're familiar with percentiles. Quartiles divides the data into 4 groups. So you have the 25th, the 50th, and the 75th percentile, basically called the first, the second, the third quartile, and then anything above it is the fourth. Why don't we put 100 here? Because if you put 100, you're basically talking about the entire data set. Quintiles into fifths, deciles into tenths, and percentiles. When you get your score for different exams, like let's say the LSAT or the GMAT, it'll tell you what percentile you were in. So let's look at a way that quartiles are used with something called a box and whisker plot. By the way, if you look at the distance between the 25th and the 75th percentile, or the first and third quartile, that is called the interquartile range. And we'll see how it's used down here. So when you're drawing a box and whisker plot, what you'll do is you'll take the highest value and the lowest value, and you'll just draw a line. There's the start of the plot. Then you'll take the 25th quartile and you'll draw a line. You'll take the 50th quartile and the 75th quartile, and there is your box. There's your lower bound, your upper bound, and that would be your median, which is the end of the second quartile, or the 50th percentile. You can also put a little dot to show where the arithmetic average happens to be. If the arithmetic average is below the second quartile line, you have data that is skewed to the left. If you're thinking about a normal distribution, it's skewed to the negative or skewed to the lower end of the range. If the arithmetic average is above the median, you have data that is skewed towards higher values. So here is what it looks like in a plot. Let's see if I can get a pen that writes on here. There's your highest value and your lowest value. Then you draw a line. Then you'll draw 3 lines. Your lowest boundary is for quartile 2, your upper boundary for quartile 3. Your median is your second quartile, and then you put a little X where your arithmetic average is. The distance between the upper bound and the lower bound is the interquartile range. Another way that it can be done is as follows. This helps you identify where the outliers are. Is you have your interquartile range. Then you'll multiply that by 1.5. Whatever value you get, you'll add to the upper bound to create that line up there, and you'll subtract from the lower bound to create that line down there. And then you have all of these little dots for different observations. Right, there's your lowest value, there's your highest value, so that you can then say, well, these probably appear to be outliers or potential outliers and may not be of much use for whatever it is I'm trying to get done. Why would we want to use quartiles, quintiles, deciles, percentiles? Rank performance of portfolios and investment managers. This is typically done in terms of quartiles. You'll see this at level 3 when you look at evaluating managers and manager selection. A whole wonderful reading on that. It depends on where managers ranked. Top quartile, second quartile, third, etc. So you rank the performance of portfolios and investment managers in terms of percentile or quartile in which they fall, typically quartile. For investment research, bottom return decile, top return decile. This also helps you set what are called long-short portfolios. So you can look at an industry and you can rank all of the companies in the industry as follows. Let's say it's globally. Pick an industry. Well, actually, we'll pick a sector like consumer discretionary. And if you look in the U.S., there's something like 140 consumer discretionary stocks that you can rank between, I think, the S&P and the Russell. And what you can do is you can then say, okay, well, the top decile I will go long, and the bottom decile I will go short, and you'll create a long-short portfolio. Another LOS with 3 keywords here: calculate, interpret, and evaluate measures of dispersion to address an investment problem. Okay, when we're talking about dispersion, we're talking about the variability around the central tendency, and we've already looked at several measures of central tendency. While the measure of central tendency, if we think about investment, while the measure of central tendency can give you an idea of the most likely return or the expected return of a portfolio, dispersion gives you an idea of the level of risk or uncertainty associated with that return. First one, the range. Really simple. Maximum value minus the minimum value. That really doesn't tell you a lot. It doesn't tell you if the data are skewed towards the upper end of the range, towards the lower end of the range. Are there more near the bottom than there are near the top? Are they concentrated in the middle? So there's no information about the shape of the distribution. Also, as you can probably guess, if you're taking the maximum minus the minimum, it's going to be sensitive to outliers. There is the mean absolute deviation, and it is exactly as the word says. You're at the very top, there's your deviation. So you have your mean, and you're looking at every observation and calculating the deviation from the mean, and it's the absolute value of it. So there's your absolute deviation. You sum them all up, divide by n. There is the mean of the absolute deviations. So this, if you didn't take the absolute value, those above the average and those below the average would tend to cancel each other out. So that's why you take the absolute value so that all the deviations are positive, and then you look at the mean absolute deviation. Sample variance is sort of the same thing, except rather than just taking the absolute value to make sure that they're all positive, you square them. So if you had an observation that was below the mean, xi minus x bar would be negative, but as soon as you square it, it is positive. So the sum, the numerator, is called the sum of the squared deviations, whereas this up here is just called the sum of the absolute deviations. Well, now we're squaring them to make sure that the positives and negatives don't cancel each other out. Divide by n minus 1. This is a bit of a problem. Why are we dividing by n minus 1 and not n? This is the denominator is called your degrees of freedom. In other words, what it's saying is that we have n minus 1 independent observations. How do we have n minus 1 independent observations? Let's say that I give you the mean, because you have it, right? And let's say that we had 20 observations. If I gave you 19 observations and I gave you x bar, you could figure out what the 20th one was. In other words, the 20th observation is not independent anymore because it will depend upon these 19 observations and the mean. So you only have n minus 1 independent observations. That's why we divide by n minus 1. It gives the sample variance better statistical properties. If we're talking about a population, if we've surveyed the entire population and not just took a sample, then we're talking about sigma squared. Our mean is mu. Here our mean is x bar. Is there a difference other than just using Greek letters versus English alphabet letters. It comes in the interpretation of what X bar and mu is. X bar is an estimate. It's our best guess of what the population mean is, whereas mu is the exact population mean. And if we're dealing with the exact population mean, we just divide by n. So when will we ever have a population? Let's say that you have a fund that has been around for 10 years since inception, and you have 40 quarterly returns. What is the variance of the fund's return? Well, you have the entire population. No need for an estimate. You will have an exact, not just an estimate of what the mean return is, you'll have the exact average return. So then we don't have to worry about working with a sample. We're now working with a population. When we calculate sample variance, notice that we're squaring. So if these are percents, we would end up with percent squared. So a variance is in units squared. We use variance because variances can be added and subtracted. And you'll see this later in the curriculum at level 2 and at level 3, especially when we look at something in level 3 called a variance swap. It's a bet on volatility, which is a standard deviation, but we use a variance within the swap because variance can be added and subtracted. Standard deviations cannot be added and subtracted. So if we have to sum a bunch of volatilities, we first square them, turn them into variances. We can add them, get the total variance, and then take the square root to get the standard deviation of that. If you take the square root of a sample variance or a population variance, you will get a standard deviation. S to denote sample standard deviation, sigma to denote population standard deviation, and it's just the square root of the variance. If the variance is all of this, that's what we have down here. It's just the square root of that. Once you take the square root, the units squared also, if you have percent squared, that disappears as well, and now you're back to the same. You're measuring the standard deviation in the same units as you measure the mean. Next, we have a category called downside deviation, and we'll look at a specific one here, target semi-deviation. There is, the basic one is called the semi-deviation, which means it is the deviation from the mean for all observations lower than the mean. That's why it's called a semi-deviation, semi meaning half. But you could have a target semi-deviation by setting some other target other than the mean below which you are interested in knowing the deviation of returns or the dispersion of returns. So let's say that you have an expected return or an average return of 6%. And over the last 20 years, you observe a bunch of values. That's how you get your 6%. It's the average of all the values you observe. But you're interested in anything below 0. What is the dispersion of the observations below 0? Here you would calculate a target semi-deviation. I'm not a big fan of using target semi-deviation because semi means half. And if you're using a target, I'd say it's a target downside deviation, not a target semi-deviation. I'm going to quibble over the use of the words here, but I'd prefer it to be called a target downside deviation. So we'll set B as some minimum level. And then what we're going to do is calculate a squared deviation and add them up, the sum of all the squared deviations for all observations less than or equal to B. The upside down A in math means for all. For all xi, observations of x less than or equal to b. Notice though, we're going to divide by n minus 1, n being the full sample n. Why would we do that? Let's say we have 20 observations and only 5 of them satisfy our requirement for being less than b. Why would we still divide by n minus 1? Why use the full sample? What the reading doesn't get into detail about is that all the others enter in as 0. So you'll have 5 values, 1, 2, 3, 4, 5, plus 0, plus 0, plus 0, plus 0 in your numerator. So you'll actually have 20 entries in your numerator. Just the ones that don't satisfy the requirement enter as 0. That's why you're dividing by n minus 1. As B increases, as your target return increases and increases towards the highest value in the data set, your target downside deviation, or your target semi-deviation, as the reading likes to call it, will increase and approach the full sample standard deviation. Next we have, actually, let me finish up with this one here. I have not found a very good use for this one as of yet. Where I do find some use in it, which I can easily satisfy by just calculating skew, by the way. Where I do find some value in it is if there is a particular stock that has momentum, it'll typically have more upside movement than downside movement. This is how you spot momentum. So you might have an algorithm that calculates the semi-deviation of a bunch of stocks you believe are under momentum. And it should have a very low deviation on down days than it does on up days. So you could just say, of the last 100 trading days, give me all days that are below 0. Well, your B is 0, and calculate a downside deviation, a target downside deviation for that. And the smaller ones are the ones that probably have a lot more upside momentum because they're well bid. But that is something you can look at in a chart. You can find in a chart. There are other indicators to find that, but that is one use for it. Coefficient of variation. Here we're going to take the sample standard deviation and divide it by the sample mean. This is a measure of relative dispersion. Every other measure we've had so far has been absolute, a measure of absolute dispersion. But they're hard to compare against each other because you'd have to have some idea of, well, what was the level of return? Typically, higher levels of return have higher dispersion. But that doesn't necessarily mean that per unit of return they're riskier. They just tend to have a wider dispersion, but it's a higher reward. So they still could be a better investment than something with a lower dispersion. So a measure of relative dispersion gives you an idea of the level of risk an investment has per unit of return, because there's our risk in the numerator, there's our return in the denominator, and our CV, our coefficient of variation, will give us a measure of risk, how much risk we're taking on for each unit of return. Obviously, the lower is the better, right? So for returns, CV measures the risk per unit of return. The lower, the better, means that there's less uncertainty and a tighter distribution of your returns. Okay, for this learning objective, notice our keywords here. We have an interpret and evaluate, measures of skewness and kurtosis to address an investment problem. Now, you will be presented with a formula for skew and a formula for kurtosis, but notice there is no calculate involved here. It's simply just interpret what the measure means or evaluate what the measure means. Okay, let's look at a normal distribution, the most common type of distribution. Returns, at least the continuously compounded returns, are modeled with a normal distribution. When you bump up against the Black-Scholes-Merton model for pricing options, you start with a log normal distribution. You take the log of that, you get to a normal distribution. And how you get to a normal distribution is you take a price, ST, divided by beginning price. That'll give you a return. You take the natural log of that. The log of a log normal distribution is normal, log normal, right? And you will get this type of distribution, which is a symmetrical distribution. It's an idealized theoretical distribution that has very well-known properties. So some of you may be saying, but, things aren't normally distributed. And Nassim Taleb, who wrote Fooled by Randomness and the Black Swan, would probably step in at this point and say, but the normal distribution underestimates risk. And yes, the normal, what we observe in the real world doesn't conform all the time to a normal distribution. So why do we use it? You have to have some starting point of something that is well understood. And then you start thinking about deviations from that starting point. And it is easier to understand a deviation from something that is well understood than to begin to describe something that is not well understood. So that's why we start from a normal distribution, because it has very defined properties that we can use. Knowing that we have deviations from this distribution, but in our minds and mathematically, it's easier to work with deviations from some theoretical perfect distribution than it would be to describe randomness. That's why we use it. It is symmetrical. So notice the highest point in the distribution here. That is our mode. The mean will equal the median will equal the mode. And it is completely described by two parameters, the mean and the variance. So if I say I have this random variable x, and it is distributed, this line that does that says it is distributed as a normal variable with a specific mean and a specific variance. If I tell you that, you know all the statistical properties of that random variable. You know what the mean of that distribution is. You know what the variance is, so you know the standard distribution. So you can calculate the probability of a variable falling below a certain number or above a certain value, because you understand this normal distribution is a very well-defined distribution with very specific properties. Let's introduce deviations from it. The first one is skew. So if you have a normal distribution, you will have a skew of 0, and as we've said, the mean equals the median equals the mode. Sometimes you will have a positively skewed distribution. This is something you'd normally see. If you see a return distribution that looks like this, chances are the portfolio included a healthy amount of long options. Because when you buy options, they either expire worthless or they pay off, and some of them pay off very big. So you might have a few of these very large returns, but a whole bunch of these small losses down here, because the long option will lose all its value if it doesn't work out. For this one, follow this simple rule. Find the highest point of the distribution. That'll be your mode. The median is always the middle, and then you have the mean. The median, if you just remember that, the median, which is the middle, is always the middle. So here, the mode, median, mean, which means the mean will have a greater value than the median, which will have a greater value than the mode. If it is negatively skewed, this usually comes from a portfolio in which you are short options. Theoretically, okay, when I say that you're short options, it means if you took a back test of, let's say, selling puts against something, and you just watched over time, you didn't actually rebalance your portfolio, you just either let the options expire or lose whatever value they had, you'd end up with a distribution that looks like this. Some big losses, but a lot of small gains. Pretty much the opposite of what a long options portfolio would look like. To be clear, in the real world, you'd never let your losses get this big. You'd step in long before this happened, and you'd minimize your loss. But here, do the same thing. Find the highest point. There's the mode. The median is always the middle. There's the mean. So in this case, the mean is below the median, which is below the mode. I think you can remember that. Median is always the middle, and the mode is the highest point. So if you're asked, given a positively skewed distribution, which of the following statements are correct? You'll have a mean equals median equals mode. Mean is greater than median, greater than mode. That you could just, in your mind, see it, and you could just draw a little picture very quickly. Say, well, the highest point will be the mode. The middle is always the median, and there's the mean. So you should be able to answer that rather directly. As I said, with the learning objective, you'll be presented with formulas. Don't bother writing these down on your formula sheet. There is no calculate. You won't be asked to calculate skew or kurtosis, just to interpret what the numbers mean. But they're presented just so you can see what's going on here. For the variance, we squared the deviations. It was the sum of the squared deviations. Skew is the sum of the cubed deviations divided by the standard deviation of the power of 3 multiplied by 1 over n. For a normal distribution, a symmetrical distribution, the numerator here will be 0. So a normal distribution will have a skew of 0. Notice that this is an approximation. This is because the 1 over n is the approximation. It is slightly more detailed than the 1 over n, but this is good enough. And your n is greater than 100. Now, it's doubtful in the real world you'll come across any type of distribution that has a perfect skew of 0. You'll have some deviation from perfection. And there is, a range under which it is acceptable, typically 0.5, anything within 0.5 of skew, 2.5 to negative 0.5 to plus 0.5 is normal-ish enough. Kurtosis. A normal distribution has a kurtosis of 3. I'll explain kurtosis when we get to the bottom of the screen. We'll just introduce the formula here. Normal distribution has a kurtosis of 3. K sub e, this is excess kurtosis. So if we have a distribution that is symmetrical, this term inside the brackets will also be 3. This whole term will settle to 3. 3 minus 3 is 0. Excess kurtosis being 0 means it is a normal distribution. So we just subtract out the 3. Why don't we do that for skew? Well, we do because it's 0. So something minus 0 is just something, right? Measures the combined weight of the tails relative to the rest of the distribution. And notice we're using a power of 4. So it is the deviations raised to the power of 4, the sum of those divided by the standard deviation of the power of 4 multiplied by 1 over n. This is also an approximation because this is an approximation here. Let's talk about different types of distributions and the type of kurtosis or excess kurtosis we'd expect to see. A leptokurtic distribution and a platykurtic distribution. The normal distribution is mesokurtic, has a kurtosis of 3. So leptokurtic has a much higher distribution around the mean, many more observations around the mean. Notice that it is underweight in the shoulders and overweight in the tails. And that is a leptokurtic distribution. And remember, it's measuring the combined weight of the tails relative to the rest of the distribution. Well, there will be more weight in the tails of a leptokurtic distribution relative to the rest of the distribution, so it will have excess kurtosis, K greater than 3. That means you are dealing with a distribution that is more peaked. It will have more observations around the mean. It'll have the mode, well, you could say the mode could be the same for the leptokurtic distribution, just a higher frequency of observations around the mean and much more weight in the tails at the cost of fewer observations in the shoulders. The platykurtic distribution is quite the opposite. There are fewer observations centered around the mean and many more observations around the shoulders. It's overweight the shoulders and underweight the tails. So since it is underweight the tails, it will have excess kurtosis less than 0. K will be less than 3. Its kurtosis will be less than 3. Its excess kurtosis, since it's subtracting 3, Ke will be less than 0, whereas here, Ke will be greater than 0. So I give it to you down here. Leptokurtic distributions, the excess kurtosis is greater than 0. For meso, it equals 0. That's a normal distribution. And for platykurtic, it is less than 0. For a leptokurtic distribution, you are overweight the probabilities in the head. More observations under the curve here. You are underweight in the shoulders and you are overweight in the tails. For platykurtic, just reverse it. If you're overweight for lepto, you're underweight the amount of observations under the curve. I call this the head, the shoulders, the tail, right? You're underweight in the head, overweight the shoulders, and underweight the tail. One key word here, interpret. Interpret correlation between two variables to address an investment problem. Notice there is no calculate here. Okay, let's start with a scatter plot. And here we have a scatter plot where we can clearly see there is some kind of linear association. However, in the scatter plot, we do see that we have an outlier. So the scatter plot is useful in identifying outliers. And the outlier, once we get to correlation, we'll see that the outlier can cause issues with correlation. It is sensitive to outliers. So it is important to identify them. Used to visualize, so the scatter plot, used to visualize the joint variation in two numerical values. Between two values, you may have no relationship. In other words, you have a scatter plot that looks like this. And clearly, there's no relationship there. A linear relationship, which we see here, or a nonlinear relationship, you may visualize something like this. Right? Clearly, we have a nonlinear relationship here. If we try to capture it in a measure of linear association, though, it's not going to do a very good job. Scatterplot matrices is to assess pairwise correlations among many variables. So let's say that we had 5 different variables. You would have a scatter plot for every pairwise association. So variable 1 and 2, variable 1 and 3, variable 1 and 4, variable 1 and 5, variable 2 and 3, 2 and 4, 2 and 5, etc. So you could look at all the pairwise correlations. That would be called a scatter plot matrix. Okay, covariance. And remember, we didn't have a calculate on our learning objective. So even though you'll be presented with formulas for covariance and correlation, you'll not be calculating any of this. So a covariance is the joint variability of two random variables. It is expressed in the same units as the variables. Remember when we talked about variance, it was in units squared, and we had to take the square root to get standard deviation. Well, a covariance will already be in the same units as the variables. And it is the sum of the deviations on x multiplied by the deviations on y divided by n minus 1. N minus 1 because we lose 1 degree of freedom. Now you may be saying, but we have 2 estimates here. We have 2 estimates of 2 different data series. If I give you the mean of x and n minus 1 observations, you could solve for the missing x. But that doesn't tell you what y is. It doesn't tell you anything about y, right? So you still have n minus 1 independent observations. So that's why we have n minus 1 here. So S sub x sub y, that's a covariance. The covariance will be greater than 0 when they covary together. That is, when the 2 variables have a tendency to display this, that the observation on x is above its mean for x when it is the same for y, when the observation on y is above its mean, and when the observation on x is below its mean, y also has the observation on y below its mean as well. So they covary together. Now that doesn't have to be a strict relationship in the data, but a tendency to display that relationship. Okay, let's introduce correlation. It measures the, and I've wrote the word down in a different color and underline it, the linear association between 2 variables. If you don't remember anything more about correlation than this, that's the important thing. It measures the linear association. So if we have this kind of observation in the data, clearly there is a strong relationship between these 2 variables, but correlation will measure a linear association. It will find a line that describes the association between those 2 variables as best it can, and it will say, well, Rxy equals 0. There is no relationship. It's not what it's saying. It's saying there is no linear relationship between these 2 variables. And we calculate it with the covariance of xy divided by the standard deviation of x multiplied by the standard deviation of y. Sometimes you'll see covariance written as S sub xy. This is the more common way you'll see it, COV and in brackets xy. That's covariance. The covariance, the numerator, determines the sign of the correlation because all standard deviations are greater than 0. There are no negative standard deviations because remember the numerator was the deviation squared. So there are no negative results of squaring something. If you square something negative, it turns positive, right? So if the correlation is negative, it had to be because the numerator was negative. The covariance determines the sign of the correlation. Properties of correlation, they range from -1 to +1. A correlation of 0 implies no linear relationship. And if we have 2 variables or 2 assets, let's say, with a correlation of 0, no linear relationship, we have maximum diversification. R equals 1 means perfect positive correlation. R negative 1 is perfect negative correlation. When we say something has a high correlation, that's not good enough. A 1 is a high correlation. A negative 1 is a high correlation. In other words, they're highly correlated, just one in a positive direction, one in a negative direction. So if somebody says to you, this variable is highly correlated with that variable, you would have to then say positively or negatively, because negative 0.9 is highly correlated, just highly negatively correlated, but that has a high correlation. The closer you get to 1 in terms of a linear association between two variables, the closer you get to perfect replication. So if we took a share of Tesla stock and we correlated with a share of Tesla stock, we should get a correlation of 1. Why? Because they're perfect replicants of each other. A correlation close to negative 1 means we have discovered a perfect hedge. So if we take a share of Tesla stock and we sell a call, or let's say we buy a put on Tesla, a very in-the-money put, which means it has got a strike price well above the price of Tesla, we will have a perfect hedge. The correlation of the movements between the two will be close to negative 1. Limitations of correlation. It measures linear association only, so it would not pick up some kind of relationship like this. It is unreliable when outliers are present, and I'll show you on the next screen what that looks like. And correlation, you must have heard this if you've taken any statistics class at all. Correlation does not imply causation. It just means two variables are correlated. So that brings up the topic of spurious correlation. So, for example, ice cream sales and crime are correlated. Ice cream sales and crime are correlated. When we see ice cream sales rise, we tend to see crime rise at the same rate. And when ice cream sales drop, crime tends to drop as well. Well, that's a spurious correlation because there is no relationship between those two variables. It is a chance relationship. Usually when you have something like this, there's a third variable at play. It could be the result of a calculation where x was divided by a and y was divided by a. That will cause x and y to pick up some relationship. Or there could be a variable a that causes x and the same variable causes y. So the summer causes ice cream sales to increase, but there is more crime in the summer than in the winter. When it's 20 below, no one's eating ice cream and no one's on the street committing crimes. So it is just that they are associated with a third variable. So when you do get something like this, ice cream sales and crime, you wouldn't say, what's the relationship there? You would say, aha, there's a third variable that's causing the increase in sales for ice cream that is also the same causal agent for the increase in crime. And if you look at it over the course of the year, you would say, aha, it's the summer. It's the weather that's doing it. Okay, let's look at our first chart on this side of the screen here. Variables with a correlation of +1. Notice that it is almost, well, not almost, it is a straight line. That has a correlation of 1. This has a correlation of 1. That has a correlation of 1. That has a correlation of 1. It does not have to be a 45-degree angle. It could be an increase of 3 units of x for every 1 unit increase in y. It could be an increase of 0.001 units of x for every 1 unit increase in y, as long as they're moving in the same direction. Here's negative. And again, this is a -1 correlation. This is a -1 correlation. This is a -1 correlation. Anything that has any kind of downward slope to it is going to be a correlation of -1. Here is no correlation at all. Clearly, you look at that, you say, it doesn't look to be any kind of relationship. Here is a very strong relationship, but it's not linear. So it would, a correlation between these two variables would be very close to 0. This is interesting over here. For all 4 charts, 1, 2, 3, 4, all 4 charts, there were n equals 11 or 11 observations in each of these charts. The average for x is 9. The average for y is 7.5 in all of these charts. The standard deviation of x is 3.2, the standard deviation of y is 2.03, and the correlation is 0.82. So if I gave you this information here, and I said the correlation is 0.82, you'd say, well, that is a very strong correlation. Excellent. Well, this chart produces those outputs. This chart produces those outputs. So does this one, so does this one. Notice we have a nonlinear association over here. We have what seems to be a linear association here. You have an outlier over here, and you have a significant outlier over here with a completely different type of pattern altogether. That is why it is important to visually inspect the scatter plot first, because just looking at this, I could say, well, I have 4 data sets and I get this out of all 4 data sets. You would say to me, you're looking at the same data set 4 times. And I could say, no, I'm not. You'd say, well, what are the chances of that happening? Well, here it is right here. Therefore, at the bottom of the screen here, visual inspection is important.